Hello, my name is Darren Holmes, and today in AC Electrical Circuits, we're going to look at lab number 5, Capacitive Reactance. So under Objective, it says capacitive reactance will be examined in this exercise. In particular, its relationship to capacitance and frequency will be investigated, including a plot of capacitive reactance versus frequency. Under reference sections, I'm referencing Sham's Outlines Basic Electricity 2nd edition. And under Chapter 14, we're going to look at capacitance and capacitive reactance. And Chapter 12 has some principles of alternating current that we need to review. So Chapter 14 starts off talking about the capacitor. Talks about the types of capacitors that we might encounter. Talks about capacitors in series and parallel and how to add them together. Talks about capacitive reactance and gives you the formula for Xc equals 1 over 2 pi Fc. Talks about capacitive circuits, capacitance only, and RC in series. Shows us the waveforms and the phasor diagrams for capacitance. And has a section on R and Xc in series, which is what our lab is about today. Nice section on impedance in series RC circuits. And a nice example of a RC series circuit and the phasor diagrams that go with it. So in the theory overview, it says the current voltage characteristics of a capacitor is unlike that of typical resistors. While resistors show a constant resistance value over a wide range of frequencies, the equivalent ohmic value for a capacitor, known as capacitive reactance, is inversely proportional to the frequency. The capacitive reactance may be computed via the formula. So we can see that Xc, or capacitive reactance, is equal to minus J, indicating that it's minus 90 degrees. And it says inversely proportional, so it's 1 over 2 pi Fc, where F is the frequency. So you can see that the capacitive reactance changes inversely to the frequency. It goes on to say that the magnitude of capacitive reactance may be determined experimentally by feeding a capacitor a known current, measuring the resulting voltage and dividing the two, following Ohm's law. This process may be repeated across a range of frequencies in order to obtain a plot of capacitive reactance versus frequency. And it says an AC current source may be approximated by placing a large resistance in series with an AC voltage, the resistance being considerably larger than that of the maximum reactance expected. So you can see under the equipment section, we're going to be using an AC function generator, an oscilloscope, and a DMM. We're going to be using the KEYSIGHT EDUX 1002G digital storage oscilloscope that has a built-in function generator. And our DMM will be the Mastech MSM 9803. We're going to be using 3 components today. So we've got the 10K ohm resistor, and on the side of the page I've given you the resistor color codes so that you can find them easily in your parts kit. We're also going to be using a 1 microfarad and a 2.2 microfarad capacitor. So these are my components for today. This is the 10K ohm resistor. Over here I have a electrolytic capacitor, and it's 1 microfarad, and you notice one leg is longer than the other. So it has a positive leg, so you have to put these ones in the right way around. The capacitor beside it is labeled 105. So that's 10 with 5 zeros after it, picofarads. So that ends up being 1 microfarad. So both of these are 1 microfarad. It's just the one in the can. has to have a positive leg, so it has to go in the right way around. Over here I have the 2.2 microfarad capacitor, and it has a long leg, so it has to go in the right way around. And over here I have another little capacitor, and it's labeled 225. So that's 22 with 5 zeros after it, picofarads. So this ends up being our 2.2 microfarad capacitor. Now when you're using capacitors in AC circuits, you should really use the non-polarized capacitors. So we shouldn't use the one in the can. So these are my components that I'm going to be using today. So using the ohm meter, you can see my 10k ohm resistor is actually 10.01 k ohms. To measure capacitance, the red lead goes in the hole with a little capacitor symbol, the black lead goes into the common hole, and the knob on the digital multimeter goes all the way around till it points to this little capacitor symbol. Make sure that you use alligator clips and do not touch the metal parts of your alligator clips because it will affect the amount of capacitance. But you can see my capacitor reads at 1.008 microfarads. And my 2.2 microfarad capacitor reads as 2.262 microfarads. So you can see under equipment, the AC function generator and oscilloscope are both the KEYSIGHT model EDUX 1002G, and I'm not going to bother with the serial number, it's not important for this particular lab. And my DMM is the Mastech MSM 9803. Now I've gone ahead and measured my components, so you can see that my 10k ohm resistor is actually 10.01 k ohms. My capacitor was 1.008 microfarads, and that was on the capacitance meter scale. And my 2.2 microfarad was actually 2.262 microfarads. Keep in mind, if you're using a non-electrolytic capacitor, the numbering on them is going to be in picofarads. So the 1 microfarad is 105, and the 2.2 microfarad will be 225. If you're using the electrolytic or can type capacitor, it'll actually be stamped on the can as 1 microfarad or 2.2 microfarad. Please also keep in mind that the resistor probably has a tolerance band of plus or minus 5%, where capacitors can be 10% or greater tolerances. We have a simple series circuit schematic, and that is the symbol for our function generator. One resistor, one capacitor that connects back to the common on the function generator. So under procedure, the first thing we're going to do is create a current source. So using figure 5.1 with V in as 10 volts peak to peak and R of 10K, we're going to assume that the reactance of the capacitor is much smaller than 10K and can be ignored. So we want to determine the circulating current using measured component values and record in table 5.1. So all we're going to be doing on our circuit is putting in our 10K resistor. This guy will be 10 volts peak to peak, and we'll assume that this is going to be a short circuit or very, very low resistance. So then V equals IR, so I equals V over R. So using figure 5.1, we're going to set our power supply to 10 volts peak to peak. We're going to have a 10k ohm resistor, and we're going to assume that this capacitive reactance is going to be close to 0. So V equals IR. I will be equal to V over R. So that's equal to 10 volts peak to peak divided by 10k ohms. So we're looking at 1 milliamp peak to peak circulating in our circuit, assuming XC is very, very small. So in table 5.1, I've recorded 1 milliamp peak to peak. So under procedure, step 2, it's all about measuring reactance. We're going to build the circuit of figure 5.1. We're going to use the 10K ohm resistor and the 1 microfarad capacitor. We're going to place one probe across the generator and another across the capacitor. So we'll be looking at VC. We're going to start with our generator at 200 Hertz sine wave and 10 volts peak to peak. We're going to put the bandwidth limit on for both channels. So this is how I've set up my trainer. You can see the red line, which is the power line coming in from the function generator, goes to the top of my 10K ohm resistor. The 10K ohm resistor meets up with the leg on my capacitor, and this is a 1 microfarad capacitor, so it's labeled 105. Then the black lead comes out, and that goes back to the common of the function generator. Now I have the yellow lead going to the junction of the resistor and the capacitor, so that's so I can read the voltage across the capacitor versus the total input voltage coming into my circuit. So I just want to show you the setup for the oscilloscope and function generator. All the black leads go together and they go to the bottom of the capacitor. Channel 2 of the oscilloscope goes to the yellow wire that goes to the junction of the capacitor and the resistor. And channel 1 of the oscilloscope and the output from the function generator go together and they go to the top of the resistor. So under procedure, step number 2, once you've finished building the circuit, the next thing we'd have to do is set up the function generator and the oscilloscope. So this is probably going to be the last time I'm going to go through a complete setup with you. So remember, this oscilloscope has been left on whatever settings the last person used was. So what we're going to do is set it up for 200 Hertz sine wave, 10 volts peak to peak with the bandwidth limit on. So we're going to do a default setup. And once you've done reading all that stuff that pops up on the screen, press it again. And we're going to select factory default. And we're going to say OK. All those warnings say it can't be undone. So we've done a complete factory default setup. So now the next thing we need to do is set up channel 1. And under channel 1, the coupling is going to be for AC. The bandwidth limit needs to be on. Fine is off, invert is off, and our probe, there it is, 10 to 1. We have to set the probe for 1 to 1. Now we have to do the same thing for channel 2. Go in through its menu, change the coupling to AC, put the bandwidth limit on, fine is off, invert is off, check the probe, and once again the probe is 10 to 1, so we're going to set it to 1 to 1. So the next thing we're going to do is turn on the wave generator, and we can see it set to waveform sine, frequency 1 kilohertz, and we're looking for a 200 Hertz signal. So we're going to select frequency, then we can use the entry knob to reduce it, and we can reduce it down to 200 Hertz. The next thing we need is the amplitude. So the amplitude needs to be adjusted, and we're looking for 10 volts per division. So that'll take a few turns. There we go. It's now on 10 volts peak to peak. Next thing we need to do is see what's actually on the screen. So my horizontal, I'm going to adjust it until I get a couple of waveforms going across my screen. Then amplitude, right? The yellow waveform, which is channel 1, is on 500 millivolts per division with the bandwidth limit on. So I'm going to adjust the amplitude control knob and I can get it down to 2 volts per division. So I can see it goes up 2.5 divisions. 2.5 times 2 is 5. So 5 volts up, 5 volts down, 10 volts peak to peak. Channel 2 volts per division. Right now it's on 500 millivolts. If I change it to 200 millivolts, okay. If I go to 100 millivolts, it goes off the screen. So I want to keep it on the screen, but I want to keep it smaller than my input signal. So the next thing I want to do is set up my measurements. So I go to the Measure menu button, press it in, and you can see at the bottom I have frequency 200 Hertz, and peak to peak for channel 1 is 10.5 volts. So now I need to get my channel 2 peak to peak voltage in there. So where it says source, I select that item and I go to channel 2. Then where it says type frequency, I want it to be peak to peak voltage, so that's up at the top. And then I can go add measurement. Okay, so now I've got my frequency for channel 1, which will be the same for channel 2. I've got my peak to peak voltage for channel 1 and my peak to peak voltage for channel 2. So that's my oscilloscope set up. So now I'm ready to go in and start taking some readings. So under procedure step 3, I'm going to calculate the theoretical value of XC using the measured capacitor value and record this in table 5.2. So in table 5.2, we have to remember the formula for XC is equal to 1 over 2 pi FC. So the calculation is 1 divided by 2 times pi times 200 times, in my case it was 1.008 microfarads. So that's times 10 to the power of minus 6. So if you're going to do 1 divided by, remember to put all of these in brackets. And the answer should be 789.46 ohms. So in step 4 of the procedure, we're going to record the peak-to-peak capacitor voltage in table 5.2. So under procedure, step number 4, we're to record the peak-to-peak capacitor voltage and record it in table 5.2. So if you've set up everything on your screen correctly, we can see a frequency of 200 Hertz produces a voltage drop across our capacitor of 900 millivolts. So under procedure, step 5, using the source current from table 5.1 and the measured capacitor voltage, determine the experimental reactance and record it in table 5.2. Also compute and record the deviation. So in table 5.2, I've recorded 900 millivolts. And to calculate XC experimental, we have to remember that V equals IR. R is equal to V divided by I. So in our case, we take the 900 millivolts and divide it by the 1 milliamps from table 5.1, resulting in 900 ohms. So you can see XC, in theory, should have been somewhere around 790 ohms, and XC experimental turned out to be 900 ohms. So under step 6 of the procedure, we're going to repeat steps 3 through 5 for the remaining frequencies of table 5.2. So in table 5.2, we're going to go from 200, 400, 600, 800, 1000, 1.2K, 1.6K, and 2K. So under procedure, for step number 6, we're going to fill in the rest of table 5.2. So make sure you do have the WaveGen menu items selected. Make sure you select frequency, increase it up to 400 Hertz, and the voltage drop across the capacitor is 460 millivolts. At 600 Hertz, the voltage drop across the capacitor is somewhere around 308 millivolts. At 800 Hertz, the voltage drop across the capacitor is somewhere around 232 millivolts. Now you'll notice the waveform is starting to bunch up on the screen, so I'm going to adjust my horizontal till it's about 200 microseconds. So at 1 kilohertz, the voltage drop across my capacitor is approximately 192 millivolts. At 1.2 kilohertz, the voltage drop across my capacitor is 160 millivolts. Now you'll notice we've jumped up to 1.6 kilohertz, so that's a jump of 4 kilohertz. And the voltage drop across my capacitor is 120 millivolts. Then our last reading is at 2 kilohertz, and the voltage drop across my capacitor is 100 millivolts. So I've recorded my results in table 5.2, and I'll come back later and do the calculations for theory, XC experimental, and percent deviation. So in step 7 of the procedure, we're going to replace the 1 microfarad capacitor with the 2.2 microfarad unit and repeat steps 2 through 6, recording the results in table 5.3. I've replaced the 1 microfarad capacitor with the 2.2 microfarad capacitor that's labeled 225 on the package. So under procedure, step number 7, I've replaced the 1 microfarad capacitor with the 2.2 microfarad capacitor, and we're going to repeat the previous steps and record these in table 5.3. Now you'll notice I've had to reduce my frequency back to 200 Hertz, and I've had to readjust my horizontal scale to 1 millisecond per division. So you'll notice at 200 Hertz, the voltage drop across my capacitor is approximately 364 millivolts. So I'm now at 400 Hertz. The voltage drop across my capacitor is 192 millivolts. Please note I've readjusted my horizontal scale to 500 microseconds and my volts per division for channel 2 to 50 millivolts. At 600 Hertz, the voltage drop across my capacitor is approximately 128 millivolts. So at 800 Hertz, I'm going to adjust my horizontal scale again. And the voltage drop across my capacitor is approximately 98 millivolts. At 1 kilohertz, the voltage drop across my capacitor is 80 millivolts. At 1.2 kilohertz, the voltage drop across my capacitor is approximately 66, 67, I'm going to say 66.4 millivolts. Jumping by 400 Hertz at 1.6 kilohertz, the voltage drop across my capacitor is approximately 50.4 millivolts. And then for our last reading at 2 kilohertz, the voltage drop across my capacitor is approximately 41.6 millivolts. Under VC peak-to-peak experimental, I've recorded all my readings. I'll come back later and calculate XC theory, XC experimental, and percent deviation. So I wanted to show you my results for table 5.3. This is with the capacitor at 2.2 microfarads. I've taken all my voltage readings across the capacitor, and you can see as the frequency increased, the amount of voltage drop on the capacitor decreased. So that was the trend we were looking for. I've gone in and calculated XC theory and XC experimental. And you can see we started somewhere around 350 to 360 ohms, generating a percent deviation of 3.5%. But as I increased my frequency, you can see the percent deviation increased until it was 19.4%. But the trend was correct, so I'm not too worried about these results. These are my results for table 5.2, and this was with the capacitor equal to 1 microfarad. I've taken all my voltage readings across the capacitor, and as I increase my frequency, you can see the voltage drop across the capacitor decreased. So this was the trend I was looking for. So as the frequency increased, XC decreased. So that was the trend I was looking for. But you'll notice in this case, I calculated 790 ohms, and I'm getting 900 ohms for a 14% deviation. And as I increase the frequency, my deviation increased to nearly 27%. So what has caused this? You have to remember that capacitance, or a capacitor, is made up of two plates separated by some kind of insulator. So in our case, when we build a circuit on a trainer and we push a wire into a connector, the wires have actually oxidized or started to rust. So as the connectors, our connectors are fairly old. Those trainers are like 30, 40 years old, so their connections have oxidized a bit. So whenever you put a wire into a trainer, there's always a little bit of capacitance between the connection. Now you have to remember that in a series circuit, when we add a little bit of capacitance, what happens is the formula is 1 over Ct is equal to 1 over C1 plus 1 over C2. So just like resistors in parallel, capacitors in series decrease the amount of capacitance. So for our 1 microfarad capacitor, we had 900 ohms on XC. When we increased our capacitance to 2.2 microfarads, you can see the resistance of XC actually decreased. So when we add capacitors in series, the capacitance decreases. So the extra capacitance added to our circuit from just the connections we used on the breadboard decreased the amount of capacitance and actually increased the amount of XC that we're seeing in our results. So the increase from 800 ohms to 900 ohms was actually caused by the extra capacitance of wiring our circuit together using the old trainers and wires pressed into the breadboards. In step 8 of the procedure, we're going to be using the data of tables 5.2 and 5.3 to create plots of capacitive reactance versus frequency. So to plot capacitive reactance versus frequency, I'm going to use my graph paper in the portrait mode. So this is what your finished graph should look like. The horizontal axes will be frequency in hertz, and I have to go from 0 to 2 kilohertz. So I'm going to do it in 200 hertz increments. And that should get me to 2 kilohertz before the end of the graph paper. XC, or capacitive reactance, is measured in ohms, and I'm going to plot that on the vertical scale. And looking at my data, I need to go from 0 ohms up to approximately 900 ohms. So I'm doing every 2 divisions is 100 ohms. So on my graph paper, every 2 divisions will be 100 ohms, so 50 ohms per division. 150, 200, 250, 300, and so on, all the way up to 900 ohms. When plotting your points, remember that the formula is XC is equal to 1 over 2 pi FC. So this is not going to be a linear relationship. It's going to be some kind of curve. So when plotting my points, I realized that this was not going to be a linear or straight line. So you kind of have to sketch it in as you go along in parts and try and get a nice curve to it. So you can see this is my line for C equal 1 microfarad. And the whole curve shifts over for C equals 2.2 microfarads. And once again, you kind of have to sketch the line in as you go along, trying to get a nice curve out of it. So this is what your finished graph should look like. As always, we have questions to answer at the end of the lab. Today we have 5 questions. I'll leave those for you to answer. When you've completed your lab, show it to your instructor so they can initial it to indicate that it is complete.